You guys can follow along here. So where are my singularities? Like here and here. Right? So if we follow the theorem, suppose we wrote a solution to this differential equation centered at -2. What if we choose x not equal to -2? What would the open interval of convergence be for the solution? Well, you think about drawing a disk, right? It would be radius 1. It would hit just bump up against the singularities above and below. And so if I looked at the sum a sub n times x plus 1, oh, I'm sorry, plus 2 to the n will converge on, -3 to -1. Let's do something a little bit trickier. What if we centered it at 0? What would the open interval of convergence for a Maclaurin series for this problem be? Actually, I'll do it over here, make it even more interesting. I'll put the x not equal to 1. Then it's kind of symmetric, right? I mean, and that's going to be the case, right? Because the complex roots come in conjugate pairs. So that kind of symmetry is going to appear in these real differential equations. But they're both that same distance. What is the distance between 1 and -2 plus I? How many over is it horizontally? It's 3 to the left, right? And it's 1 unit up. So if we go over 3 and we go up 1, what's the distance? Just as I planned, square root of 10, right? Actually, it's a coincidence. But anyway. So I'm using the Pythagorean theorem, distance, right triangle trigonometry, all that good stuff. Anyway, long story short here, if we found b sub n times x minus 1 to the n, this would converge on minus root 10 to root 10 using the theorem. I like this theorem. It makes for a nice test question that's pretty simple if you understand it. It's really not complicated what we're doing. But anyway, sometimes I spend 40 minutes talking about this, sometimes I spend 10. Apparently 10 for you guys. If you want to see me do this more, if you go back into previous iterations of this course, you'll find me blather on about this for a half hour a certain class. If you can't find it, email me, I'll help you find it. So next time we will start the Frobenius method, which you've already seen a little bit of with the Cauchy-Euler problems. So anyway, thanks guys.